Hello and welcome to our program. Today we're going to explore a fascinating frontier where language modeling, mathematics, science, and advanced neural networks converge, specifically how transformers can be extended to capture relationships in graph-like data. Think of it as a deep dive into the secret life of transformer models, discovering how this cutting-edge technology can be boosted with what's called graph-aware isomorphic attention. We'll also talk about how category theory fits into all of this. Now, before your eyes glaze over at the mention of math and graphs, I promise we'll keep this fun, easy to follow, and ultimately mind-expanding. So, let's begin. I'm excited to be joined by a special guest who specializes in bridging AI and advanced mathematics.
Thanks so much for having me on the show. I've been working on neural networks for some time, particularly focusing on graph neural networks, or GNNs for short, and how they can help transformers become even more powerful. It's an exciting time to be talking about AI. We're seeing breakthroughs in language, images, music, you name it. But behind all that, there's always that question: how does a model know which pieces of information to pay attention to? Transformers introduced an attention mechanism that's proven wildly successful. But in the research we'll discuss, we see there might be a next step: bridging transformers with graph awareness to capture relationships in more explicit ways.
Exactly. Let's first define some terms. We're going to talk about transformers. Many of our listeners might have heard of transformers in the context of large language models like ChatGPT and other generative AI. Transformers are a type of neural architecture that introduce something called attention. Attention basically identifies how strongly different words or tokens in a sentence relate to each other. With transformers, that means the model can weigh specific words more or less heavily to figure out meaning or context, like how the word cat might strongly link to fur, whiskers, or purring. In day-to-day language, attention is how a transformer decides which parts of the input matter the most at any given time.
Yes, precisely. And one of the ideas we'll explore is that attention can be interpreted as a graph operation. In a typical transformer, you have a matrix called an adjacency matrix, where each element represents the strength of connection between two tokens or items in a sequence. This adjacency matrix basically says token number 7 is strongly relying on token 3, and maybe not so strongly on token 10. Graph neural networks, or GNNs, are specialized at dealing with data that is inherently arranged in graphs. So things like social networks, chemical compounds, roadmaps, or any data that has entities and relationships in a structured layout.
So the key is to combine the best of both worlds: the sequence handling power of transformers and the relational modeling power of GNNs. Now, can you explain how that integration might work in simpler terms?
Certainly. Traditional transformers can be thought of as working with a fully connected graph in each layer, meaning every token can attend to every other token. That's a giant adjacency matrix. But the way transformers do it is quite linear. They weight the vectors, multiply them by a value vector, sum it all up, and pass it down. That's powerful for sequences, but might not fully exploit more complicated relational structures. So if you want your model to not only look at everything, but also interpret relationships more deeply, like typically done in graph neural networks, you can effectively feed that adjacency matrix into a GNN-based aggregator. For example, you might use something known as a graph isomorphism network, or GN. Graph isomorphism, in simple terms, is the question of how you know if two different graphs are essentially the same shape. A GN is designed to capture that property well, distinguishing subtle differences in graph structure. By layering that inside your transformer's attention mechanism, you might refine how those relationships are aggregated. That's how you get what's called GN attention.
I love that. And GN stands for Graph Isomorphism Network, right? That's a mouthful, but it basically means a type of graph neural network that's especially powerful at capturing whether two graphs are identical or have the same structure. So if your adjacency matrix is basically a table of who's paying attention to whom, then a GN can refine that table and learn from it in ways that a simpler linear aggregator would miss. Let's unpack a second term that might come up: PNA, which stands for Principal Neighborhood Aggregation. How does that come into play?
Principal neighborhood aggregation expands the idea of summing up neighbors. Instead of just summing, you can do operations like summation, mean, maximum, or even track variance among your neighbors in the graph. So you get a variety of signals from your immediate neighborhood. It can give a richer representation of how each node is interacting. But in practice, GIN is often simpler, and in some tasks, it actually outperforms more complicated aggregators. The research indicates that if you want straightforward, effective performance, GIN might be your best bet. PNA is definitely an interesting alternative approach that tries to gather multiple facets of your neighborhood, but it doesn't always beat GIN on every benchmark.
So we have these neural network concepts, tying them back to transformers. But I also noticed that the theoretical discussion in this research references category theory. Some of our listeners may have heard the phrase category theory in mathematics, often described as the mathematics of mathematics. Could you give a brief summary of how category theory fits into all of this?
Yes. In category theory, everything is expressed in terms of objects and morphisms, basically items and the arrows or relationships between them. One notion is a functor. That's a mapping from one category to another that preserves structural relationships. In AI or machine learning, we sometimes say that a model is a functor that takes input data to output data in a structure-preserving way. Because transformers are so general, they can be described as functors that preserve certain relationships among tokens, like grammatical or semantic structure. By adding graph awareness, we're strengthening the ability of these functors to preserve relational data. The adjacency matrix can be viewed as a morphism, specifying how different tokens relate to each other. So it's all about preserving structure across multiple domains, like language, biology, or chemistry, through universal patterns identified by the model.
Very philosophical, but it opens up the idea that transformers can handle extremely complex tasks if they incorporate the right frameworks. And category theory helps us keep the concepts consistent across apparently different fields, such as text, music, or even molecules. So let's talk about a real-world example. The paper discusses spider silk, or biomaterials, and how you might see parallels in other domains like music, right?
Exactly. In spider silk, you have hierarchical structures from molecules up to the macroscopic fibers. In music, you also have hierarchical structures, from notes to chords to phrases. The question is, are there universal patterns across these domains, for instance, repeated motifs or relationships that appear across different scales? If your AI model can identify those patterns in a flexible, abstract way, it might be better at making cross-domain discoveries or generating brand new designs. That's where the category theory viewpoint helps. It says if there are consistent relationships that hold from one domain to the next, your model can be a functor bridging them, preserving structure from spider silk to, say, a melody. It sounds abstract, but in practice, it might be used for design or discovery in ways we haven't even fully imagined yet.
Indeed. So at a nuts and bolts level, if we wanted to incorporate a GNN into transformers, we might do something called GIN attention, or PNA attention, which replaces the linear aggregator on the adjacency matrix with a GNN aggregator. Then as the model is trained, maybe on language tasks or on tasks like molecular property prediction, the model uses that GNN aggregator to capture more sophisticated relationships. So in the end, we see better performance or better generalization. Let's define generalization quickly for the audience. That's the ability of a model to do well on unseen data, not just the data it was trained on. The paper also highlights that graph-aware attention helps reduce the gap between training and validation performance, right?
Yes, that's exactly it. The experiments show that GIN attention often yields lower validation perplexity or error rates, meaning it's not just memorizing the training scenarios, but actually understanding deeper relationships. That's what many folks want from AI, real, conceptual understanding that extends to novel situations. The results also mention that these graph-aware transformers are more sample efficient. In other words, they can learn more with fewer data points. That can be a big deal in specialized scientific or engineering tasks where you can't gather a million examples. If your model can generalize from smaller data sets, it's gold in practical applications.
Practical indeed. Another piece, there is a fine-tuning approach called sparse GIN attention. This is for adapting big pre-trained models, which can be huge, to specific tasks. So instead of retraining a multi-billion parameter model from scratch, you can keep the original model mostly frozen, but add a GNN-based aggregator on top. Then you feed in the adjacency matrix from the standard attention, maybe threshold or sparsify it, turning it into something the GNN can interpret effectively. This is reminiscent of LoRa, low-rank adaptation, a known technique to cheaply fine-tune large language models. The difference is that in sparse-gen, you bring in graph logic, right?
Yes. So that's what the authors propose. If you already have a strong foundation model, like a big language model that's had massive amounts of pre-training, rather than doing full-blown training again, you just add a GNN block after the usual attention. You interpret the original attention's adjacency matrix, transform or prune it, and pass it to the GIN aggregator, scaling it with a parameter so you can tune how strong that aggregator's impact is. This approach is apparently extremely parameter efficient. You get additional relational awareness with minimal overhead, which is crucial. It's a great smaller addition that yields outsized gains in performance, especially for tasks where relationships matter strongly, like certain math word problems, scientific data, or structured reasoning tasks.
I can definitely see the appeal. Data is rarely just linear. We often have relations and knowledge graphs describing how pieces connect. This is not just relevant to material science or biology. It's relevant to social network analysis, finance, or any domain where structure is important. And the idea of bridging it all with transformers is appealing because transformers have become the go-to architecture for so many tasks: text generation, conversation, summarization, even coding. So from a big picture perspective, it means we're seeing the boundary blur between language models and graph models. It's like an AI that not only reads or listens for meaning, but also sees the webs of relationships or interactions that shape that meaning.
Yes, exactly. Now let's get a bit more concrete. Suppose you're modeling a complicated protein, so you have a chain of amino acids. Potentially, a transformer can handle that chain as if it's a sequence. But guess what? Amino acids don't only line up in a chain, they also have side chains, 3D structures, and so forth. If you approach it as a graph, you realize that certain amino acids connect or interact. Some are near each other physically, so you might feed that adjacency or proximity matrix into a GNN aggregator inside the transformer, and it might reveal deeper insights. That's the impetus for this line of research in biological or medical applications, or in language tasks. If we realize certain tokens are strongly correlated or have a lexical relationship, we can incorporate that graph. The same concept holds across many domains.
Another theme is interpretability. For many practitioners, the adjacency matrix can be visualized as a heat map or turned into a directed graph. That can show you which tokens or which nodes are linking up strongly. Then the GIN aggregator can reveal how that adjacency changes from layer to layer or which connections matter for a final decision. This can yield interpretability, or at least partial interpretability, the ability to see how your neural network is reasoning about relationships. That's quite helpful, especially in science, where black box models raise concerns.
Yep, interpretability is a key factor. The adjacency matrix is often already used to interpret transformers by analyzing which words attend to which. But now we're layering in GNN logic, which can incorporate known graph structures if we have them. For instance, you might have some prior knowledge about certain nodes being connected. That can be added in or swapped out easily in the adjacency matrix, or at least combined with the learned attention. So we get a model that's not just interpretive, but also easily modifiable with domain knowledge. That's a real plus in specialized fields like drug design, materials engineering, or high-stakes decision-making.
Let's shift gears to the broader significance. The authors highlight that transformers may be secretly GIN-like. They sort of do graph reasoning implicitly, but in a simpler, linear aggregator form. By acknowledging that and making it more explicit, we might get improved results. Or, to put it differently, a standard transformer's attention is basically building a weighted graph each time, but the aggregator is limited. GIN or PNA is more sophisticated. So that begs the question, why not always do it this way?
The biggest drawback is computational overhead. Tying GNN ops into the loop can be heavier, especially if you're dealing with a large number of tokens. Also, sometimes the standard aggregator is enough for tasks that revolve primarily around sequential or linguistic patterns. But as we push the envelope, like large-scale multimodal, multi-relational tasks, maybe we do want that extra complexity to pay dividends in new capabilities. The paper suggests it's crucial for tasks that truly hinge on deeper relational logic. If you can handle the extra cost, you get better performance.
And then we have the sparseness trick. Instead of letting every token connect to every other token, which can be huge, you threshold the adjacency matrix, so only the most important edges remain. That can reduce the matrix from something that's quadratic in size down to something more manageable, all while preserving the crucial relationships. That's reminiscent of how the human brain might prune out unimportant connections to save energy. Or the real world, where in big networks only a few of the possible relationships truly matter in practice.
That's a great analogy. Actually, it's well known that many real-world networks are sparse. Your social network definitely isn't a complete connection among all people. The power grid isn't every city connected to every other city. So imposing that structure in the adjacency matrix can better mirror real data, plus lighten computational demands. The paper describes how you can do top K or threshold-based approaches or specialized activation functions like sigmoid or sharp soft plus to build that adjacency matrix. Then the GIN aggregator only focuses on that reduced subset of neighbors.
Let's also clarify the term sharpening parameter. That means you have a scale factor that basically makes your attention distribution more peaked, so certain edges become quite strong while weaker ones fade away. It's like turning up the contrast on a photograph. That helps the GIN aggregator see a sparser but more definitive connectivity pattern, as I understand it.
Yes, that's precisely right. And it also addresses the problem of attention sometimes being too soft, distributing weights across too many tokens. If you're analyzing a big sentence or a long protein sequence, you might want to preferentially highlight a few critical relationships. The sharpening parameter basically intensifies those relationships. Then you can combine that with a threshold or top K approach to yield truly discrete adjacency. And if you want to keep it partially continuous, you can do that too. So it's quite flexible.
So I want to highlight for listeners who might be new to these ideas that in real tests, the improvements from GIN attention compared to normal attention can be substantial. We're talking about better training efficiency or better validation accuracy, especially in tasks that demand relational reasoning. This might include certain math problems or real-world data, where each input token is more like a node in a network. The moment you see that data as a graph, the synergy with GIN or PNA can be enormous. And that, to me, points to a bright future, because we often see AI usage shift from purely text-based tasks to multimodal tasks, knowledge-based tasks, and beyond.
Completely agree. And I think one of the biggest success stories might be in specialized fields. For instance, in drug discovery, you always deal with molecules, which are graphs of atoms. If you combine that with textual descriptions of what a drug's supposed to do, you have a multimodal environment. The synergy of transformers for text and GNN for molecules has always been something people talk about, but bridging them in a single architecture so seamlessly is quite groundbreaking. We can also foresee potential in fields like robotics, where the environment can be partially structured as a graph of objects, states, or possible actions, and the language instructions are sequences. The sky's the limit.
Absolutely. Now, to pivot a bit, I saw references to an interesting concept: hierarchical GIN modeling inside a transformer. The idea that a transformer is already kind of a graph aggregator across layers, so we can nest GIN inside each head, then combine them at a global scale. This is advanced stuff, but the upshot is that we build a multi-scale representation of connectivity. I guess that's reminiscent of hierarchical structures in biology, or multi-level analysis in social science, or fractal patterns. Do you see a future in a general-purpose AI that can unify many layers or many forms of hierarchy in a single model?
Yes, definitely. That's the dream. Right now, we do a lot of specialized engineering. We have a GNN for a certain domain, a transformer for a different domain, or we do some patchwork to combine them. But if you unify them into a single architecture that can natively handle sequences and relational data in a hierarchical manner, you get a Swiss Army knife of models. Something that can reason about local relationships, like a single measure of music or a single patch of a molecule, but also global patterns. That opens up new possibilities for interpretability, for introspection, and for reusing knowledge across tasks. The discussion about category theory suggests that we're heading in that direction because it focuses on how structure is consistently managed across levels. So yes, I see big potential here.
Let's bring in the concept of an information bottleneck. This is the idea that a model shouldn't hang on to everything, otherwise it overfits or uses too many unhelpful details. It should compress information down to what's essential for predicting the outcome. So in the graph sense, we probably want to keep the key edges and filter out tangential or redundant connections. That too can improve generalization, a not so trivial task in machine learning. So it's not just a question of capturing more detail, but capturing the right detail in the adjacency matrix.
Yes, exactly. And that's why you see these techniques like thresholding, top K, or sigmoid-based transformations. It's about removing unneeded clutter. Only keep the edges that matter. Then the aggregator, like GIN, can do its job effectively because it's focusing on the truly relevant subgraph instead of everything. This is especially important for large N, meaning if you have a big input sequence or thousands of nodes. Without filtering, your adjacency matrix might blow up in size, and you'll either run out of compute resources or your model will get stuck focusing on unimportant details.
Very well put. And from a software standpoint, a lot of these methods can be implemented on top of existing transformer code, because that adjacency matrix is already computed as part of the attention mechanism. The new approach basically says, okay, now that we have it, let's do more with it, feed it to a GNN, or we do the thresholding, etc. Maybe it's not trivial to implement, but it's also not building something from the ground up. This is an evolution of the standard pipeline, which I find encouraging for future open source or mainstream adoption.
Totally. That's one reason the paper included an approach to do it as a fine-tuning strategy. They called it sparse GIN. If your base model is enormous, you certainly don't want to start training from scratch with a brand new aggregator. Instead, you just freeze the base, interpret the adjacency, do a bit of sparse thresholding, add a GNN block that has just a fraction of the parameters, maybe a small fraction, and train only that block. That's parameter light. It's not that different from LoRa, but with a graph twist. People in the community want these parameter-efficient fine-tuning approaches, so it's definitely on trend.
I can imagine a domain scenario. Maybe you have a base language model trained on general text, and now you want to adapt it to a specialized chemistry domain. You can feed in adjacency knowledge about molecules, or let the model read chemical descriptions that form adjacency patterns. Then the GIN aggregator learns those patterns. Rather than throwing massive computational resources at the entire model, you keep almost all of the original parameters, focusing on that extra aggregator. This technique might also be good for limited hardware labs or teams that don't have the budget to operate massive GPU clusters.
Absolutely, that's the big selling point. Another is interpretability, as we mentioned. The adjacency matrix is not random. It's based on the attention scores, which themselves are interpretable. So you can see how the model is focusing on certain relationships, like an amine group interacting with a specific domain in a protein, for instance, and then how the aggregator transforms that snippet of adjacency data to produce a final prediction. That can be quite helpful for domain experts, too.
Let's shift to some real numbers or results. The research indicates that when we compare standard transformers with GIN-augmented transformers on some tasks, we often see that the GIN version not only has lower training loss, but also a significantly lower validation loss, which is that measure of how well the model generalizes. Also, the difference or gap between training and validation is smaller if you do GIN, meaning less overfitting. And interestingly, the paper found that if you go with PNA-based attention, it's not always better than GIN. So GIN might be the simpler and more reliable solution, at least from these experiments.
Right. That's consistent with the idea that GIN is extremely good at capturing whether two graphs are isomorphic, i.e. structurally the same. It's almost ironically simpler than PNA, but often more potent. PNA wants to gather many aggregator signals like sum, mean, max, variance, and that can get complicated or over-parameterized. The simpler GIN aggregator sometimes generalizes better, producing a more stable result across tasks. Obviously, that might change with different data sets. But that's the gist of the results here.
It's probably also worth reminding the audience that transformers rely heavily on multi-head attention. Each head represents a different perspective or lens on the data. So if each head is now a GIN aggregator, we can get a multi-view representation. Then we can combine them across heads and feed them into a feed-forward MLP, or MLP stands for multi-layer perceptron, basically a small neural network that can do further processing. That layering might create a synergy that's quite powerful. The paper even calls it hierarchical GIN, because you have GIN inside each head, and then you combine them globally with yet another aggregator.
Yes, exactly. And it's that synergy that probably leads to the improved generalization. The multi-head approach is basically parallel streams of relational reasoning coming together in a single model. If each stream captures a different angle, maybe one head focuses on local adjacency, another on global adjacency, and so forth, that's how the model can unify those insights. It's also reminiscent of how some people interpret the brain as modular in its reasoning, with specialized modules that integrate information at higher levels.
Let's also talk about the potential to incorporate external adjacency matrices. Sometimes you have domain knowledge, a known underlying graph, like say a map of social or biological interactions. You might just feed that knowledge in as well, so that the model doesn't have to discover it from scratch. Then you might blend the discovered adjacency from the softmax attention with the external adjacency from your domain knowledge. Have you seen that done in practice?
It's definitely proposed in various papers. The idea is that you take the adjacency from attention and add or combine it with the adjacency from your known knowledge graph. If the knowledge graph says certain nodes must be connected because of physical laws or known constraints, you can inject that in. Then the aggregator takes that combined adjacency as input. This is huge for interpretability and compliance with real-world constraints, because you can't have the model ignoring the laws of physics or known biomedical facts. It's a strong advantage if you want to build specialized systems.
That leads us to something bigger, AI for science. Whether it's discovering brand new materials, analyzing spider silk, or bridging the gap between biology and music, these advanced transformers, like GIN attention models, are opening new doors. Possibly they can unify data from very different modalities under one roof, going beyond typical language tasks. The dream scenario is a single system that can read about a new chemical compound, reason about its molecular structure, figure out potential applications, and even generate new variants. But to do that effectively, you need to handle both the linear textual representation, like a text description, and the nonlinear relational representation, like a molecular graph.
Yes, that's the future many of us are hoping for. And the combination of GNNs with transformers is a key step. Some might think we just need bigger and bigger transformers, but that's not always the best approach. The real improvements might come from more specialized architectures, or adding conceptual tools like GIN that have proven themselves in other contexts. That's how we get synergy, rather than just blindly scaling up the same architecture. So that's exciting from a research standpoint and for real-world applications.
Nice. So we've said a lot, or at least enough to give folks a sense that transformers plus GNN is a marriage of two powerful methods. We've covered GIN, PNA, adjacency matrices, attention, category theory, multi-head expansions, and more. Maybe it's time to start wrapping up with some final thoughts or big takeaways. Let me ask you, if you had to pick the single biggest benefit of adding graph-aware attention to transformers, what would it be?
My personal pick is that it addresses a deeper conceptual limitation of plain transformers. Transformers are so good, but they originally revolve around sequences, ignoring a lot of structure. By rethinking them as graph-based, or at least giving them graph-based capabilities, we open new horizons where any domain that's best modeled as a network of relationships is in scope. That's a big leap in bridging from just text or 1D data to something more general. So I'd say that's the biggest benefit.
That's a great one. For me, the highlight is the fine-tuning approach, the notion that we don't have to break the bank to get a big model to do new tasks that revolve around graphs. We can just add that aggregator module, feed it the adjacency matrix, and get better performance on specialized tasks. That synergy is right in line with the real needs of many labs, startups, or academic groups. So that's my big takeaway. Well, it's time for us to round out the conversation. Let's do a quick summation of the main insights for our listeners.
Absolutely. First, transformers rely on attention, which can be interpreted as building a graph among tokens. Second, graph neural networks like GIN can replace the simpler aggregator in attention to capture more complex relationships. Third, this leads to better performance and generalization in tasks that rely heavily on relational data. Fourth, category theory helps unify these ideas under a single framework, preserving structure across domains. Fifth, we can do this from scratch in pre-training, or we can fine-tune a big, already trained model with a sparse GIN approach. That's essentially the gist of it, and it's a major step for bridging sequence-based and graph-based learning.
Thank you. And I would add, because real-world data often has inherent relationships, graph-aware transformers are likely to show up more in areas where domain knowledge or advanced relational structure are crucial, from biology to finance to multi-agent systems. The synergy is huge. So that's all for today's conversation. Thanks to you for providing such a clear and detailed explanation, and thanks to our audience for tuning in. We hope you've learned something new about how AI can be taken to the next level by fusing graph relational understanding with the flexible power of transformers. Until next time, goodbye.